Hi everyone. In this lecture, I'm going to discuss something about the bandgap reference. So in our analog circuit design, the BGR circuit is very important for us because it gives us the constant reference voltage. That's mean if we have a BGR circuit, this one is VSS, and it gives us a constant reference voltage which is not dependent on VDD, temperature, and the process. So first, let's figure out that how to get a temperature independent voltage. So that's mean to get a temperature independent voltage, we require two kinds of voltage. One is PTAT, the second is CTAT. The PTAT stands for proportional to absolute temperature. That's mean voltage is rises if we increase the temperature, which is called PTAT. On the other hand, if we increase the temperature, the voltage is false, then this type of nature is called CTAT, which is means that's complementary to absolute temperature. And this slope is positive and this slope is negative. So if we have these two kinds of voltage and as we add together, that's mean this one is PTAT, on the other hand this one is, if we add together then we can get, so this our Vref. So if we add together then we can get a reference constant reference voltage. So that's mean Vref equals to VCTAT, and this should be del Vref by del T equals to 0. So that's mean if we have a slope of PTAT we need same slope with opposite direction. That's mean if we have a slope of the PTAT which is 1 millivolt per Kelvin, we need opposite slope which is 1 millivolt per Kelvin to get a constant reference voltage. How can we generate these kinds of PTAT and the CTAT voltage? So if we look a forward bias diode, that's mean we have a diode which is biased with some current, let's say, which is ID, and this one is D1, and this voltage is called VBE, and this one is obviously VDD. As this diode is in forward bias, we can get a VBE voltage which is approximately 0.6 to 0.7. We can also use, instead of this diode, BGT, right? Okay, that's why it's called BBE. As we know that this current ID equals to IS, which is reverse saturation current, e to the power BBE by BT minus 1. Is e to the power BB by BT. We can ignore this minus 1. So finally, we can get that the VB equals to VT ln ID by IS, and which is approximately 0.6 to 0.7. So here is two terms. One is VT and the another term is ID by IS. And our aim to find these two types of voltage. One is CTAT, another is the PTAT. So if we look at this term first, this VT, that's mean the thermal voltage VT equals to KT by Q. And if we take this Vt by del T, and we can get that K by Q, and as we know that the Boltzmann constant is 1.38 to the power minus 23 joule per Kelvin, right? Also the Q is 1.61 into 10 to the power minus 19 Coulomb. So if we put this value, and we can get the slope, which is approximately 86 86 microvolt per Kelvin, and the slope is positive. That's mean this term is behaves like a PTAT, and as we can see that here is a term which is strongly dependent on temperature. So if we increase the temperature, this means if we increase the T, the Vt will goes up. That's mean this Vt is a uh, PTAT nature. And the slope is 86 microvolt per Kelvin. And as it is temperature, this volt, and this one is the PTAT, which is comes from the thermal voltage, and the slope is 86 microvolt per Kelvin. Okay. Also, if we take a look on this at this term ID by IS, so let's take if we take this Vt for the room temperature, this means the Vt at 300 Kelvin, which is 86 microvolt into 300. Obviously, this is microvolt per Kelvin and Kelvin. So finally, we can get that 26 millivolt. So if we take a look on this term, as we know that from the device physics that the reverse saturation current I is equals to I naught into e to the power minus BG by BT, and here I naught is constant, and This is technology dependent. Also the BBG, which is bandgap voltage, and for silicon, which is roughly 1.1 to 1.2 volt, and BT is the thermal voltage, as you know, which is 26 millivolt at 300 Kelvin. Okay, so for the previous expression, what we get that VB equals to, and we can put this expression is to there, so we can rewrite it that, so I naught into e to the power minus VBG by VT. So if we simplify this expression, so finally the BBE equals to, we can get this expression. And we can also rewrite this expression as that BT ln ID by I naught equals to BBE minus BBG. Okay, so if we take the derivative with respect to temperature, that's mean also this term is also zero because there is no temperature dependent terms. So that means this will also 0. Okay. So finally, if we replace this equation k by q, let's add t in again in here and let put t in reciprocal. So ln id by I naught. So we can say that Vt ln id by I naught equals to what, this Vbe minus Vbg, right? Vbe minus Vbg, this term by t. And if we put this value 0.65 minus 1.12 divided by 300, so we can get that 1.56 millivolt per Kelvin. Basically this one is negative. So if we plot, so if we increase the temperature, the voltage will down, right? And the slope is minus 1.56 millivolt per Kelvin. And some textbooks it's minus 2 millivolt per Kelvin. And this called the CTAT, complementary to absolute temperature. If we recall the expression, the forward voltage of the diode, here is the two term, one is the PTAT and another term is the CTAT, right? But which is dominant factor? This one is uh, 86 microvolt, and this slope is 86 microvolt per Kelvin, and this slope is minus 1.56 millivolt per Kelvin. So obviously this one is dominant. As we plot this slope of this voltage, that will look like a CTAT voltage. That's mean obviously here is the two terms. One is the PTAT and the CTAT, but the dominant factor is the CTAT. That's why we get these kinds of CTAT voltage, which slope is minus 1.56 millivolt per Kelvin. But this in reality, in practical case, the slope is not like linear. There is some non-linear effect. The CTAT is dominates, but as we need the reference voltage, we need the same CTAT as the PTAT. How can we get that? Let's say if we take one CTAT, that's mean the collector current IC1 equals to, no, let's figure out this voltage, which is BBE1, and let's say another voltage BBE2, and this current is IC2. So the BBEE1 equals to, and the BBE2, so if we add together, that's mean let's say BBE1, that's mean we are going to add together and taking this voltage, and which is called BB1 minus BBE2, and this one is called del BBE. So this one is del BBE, and this is, in this case, what is the condition the IS1 and the IS2 same? And if as we know that the reverse saturation current is very much depend on the devices, that's mean if we take the Q1 and Q2 equals to same area, that's mean Q1 equals to Q2, and here is the IS1 should be equals to IS2, right? So basically our target is to make some difference in this, make some difference in voltage in this node. In case 1, in case 1, that's mean the IC1 is not equals to IC2, and the IS1 is equals to IS2, and this is possible to make the Q1 equals to Q1 to the area of these two VGTs are same size, right? And the del VBE is now the VT ln mm, IC1 by IC2, because that if the IS2 equals to IS1, this will be cancel out, and finally the del VV equals to VT ln IC1 by IC2. And if the IC1 equals to M times IC2, then we can say that the del VV equals to VT ln M. We can change the current of IC1 by changing this multiplying factor M, and by this multiplying factor we can also change the voltage difference of this two node. Okay, also in another case, let's say in case 2, that the IC1 is equals to sorry, this will be looks like in IC2 is equals to IC1, and the IS1 is not equals to IS2. That's mean Q1 is not equals to Q2. That's mean the size are different. And for this case, you can also say that if the IC2 are the same, so we can say that Q2 equals to M into Q1. That's mean the IS2 equals to M into IS1. So we can say that the del VBE equals to VT ln IS2 by IS1 also, which is VT ln M. So by changing this multiplying factor, we can make some voltage difference in between these two nodes, and what it represents in circuit. Let's say to apply this equation in circuit, let's say and we can sense the del VV by changing this M. That's mean, but the current is same, right? The IC1 equals to IC2. And the difference between this two nodes is a del VB, and the difference is we are not taking one uh, BGT, rather than in this node we are taking M times of BGT. That's mean QM, and this voltage, the VBE1 minus BBE2, that's mean which is BT ln N is a PTAT voltage. So we can increase the slope of this PTAT by changing this multiply factor M, because as we see that in previous equation, this is a dominating factor. That's why if we take, there is M times of BGT, and then we can generate this PTAT voltage. So from this only one we can generate the CTAT, and by this difference we can generate this PTAT voltage. But here also some problems, like if we take this derivative with respect to the temperature, this mean and at 300 Kelvin 25 millivolt, 300 Kelvin ln n by 12. So to get a 2 millivolt per Kelvin, so as we want to make the same slope, right? To make the same slope as the CTAT, which means we need positive 1.56 millivolt, or some in textbook, as it is in, let's say, 2 millivolt minus 2 millivolt. So if we want to take positive 1.56 millivolt, or let's say positive 2 millivolt slope for this PTAT, how much M we need? So let's say, by the way, this one is M, the number of BGT. So to get, let's say, 2 millivolt, that's mean plus 2 millivolt per Kelvin, the required value for the M number of parallel BGT ln M by 12 equals to 2, and M equals to e to the power 24, and this one is too much. So how can we reduce this number? We can add some constant. Let's say as we know that this one is the Vref. So we can compensate this PTAT to make the same slope for the CTAT, to add some parallel diode by changing the number of M, but we require very too much numbers of parallel BGT. That's why If we add some constant in here, we can reduce this number. So that's mean the B out equals to BB1 plus K is a constant that will reduce this number of parallel diode BT ln n, and this one is CTAT, and this one is the PTAT. So let's see the temperature dependency. Uh, the final value should be like del V out by del T equals to 0, right? That should be 0. So this our target. So if we say that if we put this expression, this mean previously we calculate that, sorry, let's say is del by del T BB1. Previously we calculated this value, and this value is like minus 1.56 plus del by del T, and this one is that mm, K BT ln M, right? And this one plus K BT by T ln M. And obviously this one is a 1.56 milli. So finally this one is a 0 point, and finally this one is 0.468 volt. And this term value, right? So if we add, that's mean B out equals to BB1 plus K BT ln M. This one is what? 0.65 plus 0.468, and finally we can get the band gap voltage 0.1.12, 1.12 volt. So by doing this we can generate the band gap voltage. So our final block diagram is like with which multiplies with some multiplying factor and then add it to, and then we can get the B ref, and which is Kp, which is a multiplying factor or some gain with B PTAT. And next video I will cover with some circuit example. Thank you for your time.